Okay, well, it's time to get started. So welcome to the Homotopy type theory electronic seminar talks. We really need to come up with a good acronym for that. So we're all experts now, so just a couple of brief reminders. As usual, we're going to record the talk, and if the speaker agrees afterwards, we'll post the video. If you want to ask a question, just unmute your microphone and interrupt the speaker, but then make sure to remute your microphone after you ask your question. Talk will go for approximately 60 minutes, and then we have up to 30 minutes for questions. And that's all the reminders I want to give, so I'll just introduce Mike Shulman from the University of San Diego, who will tell us about type 2 theories.
Thanks very much, Dan. I'm very excited to have this opportunity. These electronic talks have been really great, and I think they're going to do really great things for the field. So thanks, since I have this opportunity, thanks to Dan and Chris for organizing these very much. So I want to tell you about a project that Dan, Licata, and Mitchell Riley and I have been working on. We've been working on it for maybe 3 years or so now, I think. So we've come a long way, and we've sort of had partial results along the way. And so we've gotten to the point where it's a little bit complicated. And so I'm going to try to build up in stages to where we are now through the stages that we've gone through. And I also want to start with some motivation so that maybe you'll be interested in sticking with us through it all. Since I'm a category theorist, I want to start with some category theoretic motivation, which is sort of where I came from and why I'm interested in homotopy type theory. This has to do with its interpretation as an internal language for higher categories, and particularly for infinity one toposes. And this is a statement that tends to get bandied around in different ways, that homotopy type theory is an internal language for infinity one toposes. And it's not always clear exactly what its formal status is. So I'd like to propose that one way to consider its formal status is as a hypothesis. And I mean this in an analogous sense to some other hypotheses of higher category theory. Those people who follow higher category theory may have encountered these before: the homotopy hypothesis, the stabilization hypothesis, the cobordism hypothesis. And these sort of big ones, at least, were introduced by Buys and Dolan and I use the word hypothesis as a way of indicating that it was not precise enough yet to be a conjecture, so that once we have definitions of the relevant words involved, then we can try to prove it as a theorem. But on the other hand, we could also consider it as a desideratum for our definitions, that they would support the proof of such a theorem. And in this case, the definitions of words that might include things like homotopy type theory. What exactly does that entail? What sort of type operations? What sort of structure? And even infinity one toposes, we know sort of what some of those are, but we don't have a general definition of an elementary version. So, I mean, I'm not going to go through all of these here, but I just threw up here a list of some things that we know, which are sort of partial results in the direction of proving this hypothesis precisely. Some precisely stated conjectures that we would like to prove, which are sort of incarnations of this hypothesis, and questions or definitions that we're working on making, which are sort of motivated by wanting this hypothesis to be true. Particularly, for instance, we want a definition of what is a general notion of higher inductive type. We'd like it to be such that it's supported in these higher categorical models, assuming that they exist, that we can prove the conjecture. And also, if we want to make a definition of something like an elementary higher topos, we'd like it to be such that it supports this homotopy type theory as its internal language. And one reason that I bring this up is because I want to repeat a point which I frequently like to make, which is that we should be thinking about more than one model. I think it's great to think about particular models and to start with particular models, and particular models may have nice formal properties syntactically or semantically. But I think it's important to keep in mind that we should not be limited to a particular model, that it's not enough to have one model. We ought to want to have lots of models. We shouldn't think about there being one model which is the intended model of the theory, I think that we should intend to have many models. There may be a motivating model or a canonical sort of model that we started with, but we should try to generalize beyond that. And one reason I feel so strongly about that is that I think just for the health of the subject, it's good to have applications and sort of to convince other people that it's a useful theory. And I think those applications to algebraic topology and classical homotopy theory are much closer if we go through models other than sort of classical ones like simplicial sets, if we think about higher toposes. And sort of, we've already seen examples of this for instance, in the Homotopy type theoretic proof of the Blakers-Massey theorem, which has then been interpreted in infinity toposes and already found generalizations in its Goodwillie calculus, sort of beyond its original context. And sort of the higher topos theoretic perspective is crucial, I think, for those sorts of applications. So my motivation for this, sorry.
Can you give a reference for that real quick? I mean, sort of the hot model that's relevant to Goodwillie calculus.
So this is really sort of a conjectural model again, because we don't have complete models in all higher toposes, but I don't have a top of my head what the particular model, but the paper I'm referring to is the one by Eric Finster and Joyal and Anel and Biederman, I think. I see Dan nodding, so that's probably it. That was in the last couple of years. I don't remember the name of it, but it's like a generalized Blakers-Massey theorem. And they use the language of higher toposes to state that result, but it's their approach and their motivation is directly comes from the higher topos theoretic version of the Homotopy type theoretic proof of the Blakers-Massey theorem. Does that answer your question? I'll assume that's a yes.
Yeah, great, thanks.
Okay, so this is my motivation for the work that we're doing right now. But before I sort of move on to the specifics of this, I want to say a little bit about what a higher topos is for the type theorists in the room who may not be as familiar with it. So from one perspective, if you're a type theorist, you can take this hypothesis as sort of a working definition of an infinity one topos, that it's a collection of objects and morphisms that can interpret the Homotopy type theory, if you know what that means. But it's useful to have examples in mind other than this sort of tautological version. So in addition to here I'm talking about examples that are constructed inside of a classical theory, just to be clear here. We'd like to be able to construct these inside of homotopy type theory as well, but that's again, one of these sort of conjectures and hypotheses for the future. So in addition to the sort of the standard model where the types are interpreted by infinity groupoids or spaces in the sense of homotopy theory, which is sort of the infinity version of the category of sets. We replace sets by infinity groupoids when we categorify. We can think about pre-sheaf toposes, pre-sheaf higher toposes, pre-sheaves of infinity groupoids, or we can think about sheaves on some site in general, or more particularly sheaves on some topological space. And these are sort of all just higher categorical versions of standard one topos theoretic constructions, if you're familiar with that. The situation for functors, which is sort of relevant to what I'm going to talk about today, is a little bit subtler, and the intuition of it just being a model of an higher topos being a model of type theory doesn't really get us quite to the right notion of functor that we want, because there are actually two different, this is already familiar from ordinary one topos theory, there are kind of two different notions of morphism between topos. On one hand, there's a logical functor which preserves all the relevant structure, and this is what you would write down if you're just thinking about a topos as a model of type theory, that it sort of has all this categorical structure that corresponds to the type theoretic structure, and the functor just has to preserve it all. But sort of more commonly encountered in nature are what's called a geometric morphism, and this is an adjoint pair of functors where the left adjoint, P upper star, preserves finite limits. And the right adjoint, of course, also preserves all limits because it's a right adjoint. And these appear all over the place when we look at these examples. For instance, a functor between small categories induces a geometric morphism between their pre-sheaf toposes by right con extension and restriction. A continuous map of topological spaces induces a geometric morphism in the same direction between sheaf toposes. Any Grothendieck infinity one topos has a unique geometric morphism to sort of the base, the canonical one of infinity groupoids, where the right adjoint takes the space of global sections, maps out of the terminal object. Then the left adjoint constructs some sort of discrete or constant object. And sort of these appear all over the place in higher topos theory. And in fact, a lot of the interesting theorems about higher topos theory are not about just one topos, but about diagrams of toposes and geometric morphisms between them. So I just threw up a few examples here, like connectedness, or local connectedness, compactness of a topos are all expressed naturally in terms of the geometric morphism to the category of sets or infinity groupoids, and other sorts of modalities and monads and monoidal structures and so on have to do with functors between toposes. And so if we're thinking, if we're motivated to study higher homotopy type theory as an internal language for higher toposes, then it's natural to ask, can we generalize this internal language hypothesis to apply not just to single higher toposes, but to geometric morphisms between them? And that's sort of the point of the project that we're working on. And the short answer is that although we don't have all the details worked out yet, we claim the answer is yes. And these functors, p upper star and p lower star, and sort of more general kinds of functors between higher toposes and higher categories appear inside the type theory as a generalized notion, sort of higher modality. So there's a certain simple kind of modality that appears in the Homotopy type theory book, which is a monadic idempotent modality on a single higher topos or higher category, a category of types, a universe of types, but we can sort of talk about more general modalities in type theory, and that's how we see these functors appearing. Although, as I said, we're still working on the fully general dependently typed version, we've already seen examples of this appearing in lots of different applications of particular versions of this theory for particular kinds of functors or particular geometric morphisms. So the first one was cohesive type theory and real cohesive type theory, and which we have three modalities that talk about the shape and the discrete objects and the co-discrete objects. There's differential cohesion that a bunch of us were working on at the MRC and have continued working on. In this case, we have 6 modalities. In addition to the cohesive ones, we have 3 more. Recently, there's this paper by Dan Licata and Ian Orden and Andrews Pitts and Bass Spitters, where they use one modality as a way to construct internal universes, sort of generalizing the construction of the Kahn universe in cubical sets. And there's other work in progress involving parametrized spectra, in which we have a monoidal structure, and we have a modality that is adjoint to itself, and incorporating things like opposites and groupoidal cores into directed type theory, which Emily talked about here a few weeks ago. So there are lots of applications that people are already working on, and lots more applications that sort of have in mind potentially. And I think it's really useful even when thinking about any of these particular applications to have a general framework in mind. For instance, maybe if you have one modality or even 2 or 3 modalities, you might be able to come up with the type theory for that, just sort of following your nose. But if you have 6 modalities, then it's really helpful to have a general theory to point you to the right direction. So that's it for our motivation. Let's move on. So as I said, I'm going to build up in stages. So let's start by thinking about the simple case where we have one geometric morphism. So this is a pair of adjoint functors in opposite directions between 2 higher toposes. And so just naively, how might we try to model this with type theory? Well, we have 2 categories, and each category we can think of as being the model of a type theory. So we can imagine maybe we have an E-type theory on one side, and we have an S-type theory on the other side. And then we have operations that go between them, just like functors between our categories. So we have a P upper star that makes S-types into E-types, P lower star that makes E-types into S-types. And then we add extra stuff that makes them functors. So we would need rules that make them functors, and we need rules that make them adjoint to each other. And then because these are higher categories, we need to know them they're functorial on higher homotopies, and we have coherence laws relating them to the adjunctions and these sort of higher coherence laws and so on, and this gets very complicated. And if it's not impossible to sort of write down all these coherence conditions, Emily and Dominic did it in one context, and there are various other ways that people have talked about coherent adjunctions between higher categories, but it'd be nice to avoid having to build all of that into our type theory. And there's a general approach to doing this. In fact, there's a general approach to avoiding coherence questions in category theory, and also a general approach to avoiding coherence questions in type theory, which at sort of fundamentally are really doing the same thing, even though they look kind of different and they're phrased in different language. So on the one hand, in type theory, there's a general principle that types should be defined by introduction rules, elimination rules, and sort of computation and uniqueness or beta and eta rules. And when we define type theories like that, they generally satisfy good type theoretic properties like canonicity and normalization and so on. And whereas in category theory, we generally try to define objects by universal properties. And one reason to do that is that a type defined by universal property often tends to be automatically fully coherent, so we don't need to throw in the coherences by hand. So for instance, you contrast the notion of a monoidal category, where we have to put in the associativity isomorphism and the coherence laws for that explicitly as structure, versus the notion of a category with finite products, where we just give the product objects with a universal property, and then all the coherence and associativity comes for free by the universal property. And these are phrased in these sort of design principles for type theory and category theory are phrased in different language, but I claim that they're fundamentally, in most cases at least, they're doing essentially the same thing. And to convince you of that, let's talk about the case of products. So for the universal property in category theory I'm going to break it down into 4 pieces. So on the one hand, there's the saying that we have the projections from the Cartesian product. So that's the first part here. And that corresponds in type theory to the elimination rule for the product type. Then there's the factorization property that says that given a map from X into A and B, I get a map into the product. And that's corresponds to the introduction rule in type theory, the pairing operator. And then we have to say that factorization has the correct composites with the projections, that it gets us back the maps we started with. And that corresponds to the beta rules, the computation rules. And then we have to say that factorization is unique, and that corresponds to the eta rule, or the uniqueness rule for products in type theory, that every element of the product type is a pair. Okay, so these 4 ingredients in a type theoretic package correspond to the 4 ingredients in a category theoretic universal property. And that appears sort of all over the place in categorical semantics of type theory. So our goal here is to leverage this idea to describe these adjunctions. And so what we need for that is we need a universal property for an adjoint pair of functors. And of course, an adjoint to a single functor has a universal property, but to express that, we have to already be given the functor. So what we'd like is a collection of data which will determine both of the functors in an adjunction by universal properties from the same underlying data. And a good way to do that is to talk about a profunctor, which is also called a distributor or a bimodule or just a module. This definition of a profunctor that I have here is a little bit non-standard, but it's going to be the one that's most convenient for generalizing. So I'm going to define a profunctor between 2 categories or higher categories to be another category H together with a functor from H to the category with 2 objects and 0 and 1 and 1 non-identity arrow between them. This is the Blackboard Bold 2, the arrow category here. And I require that the fibers of this functor over the object 0 and 1 are the categories S and E that we started from. Okay, so in addition to the fibers, the only remaining data in this category H is the morphisms from objects of S to objects of E, because these are the ones that lie over the morphism from 0 to 1. There are no morphisms in the other direction in H because there's no morphism in 2 for them to lie over. And these morphisms lying over this non-identity morphism in 2 are sometimes called heteromorphisms because they're morphisms from an object of one category to an object of a different category. Hetero means different. And the composition operation in the category H gives us an action of the objects in E and S on these heteromorphisms. And this is equivalent to other definitions of profunctors that you might have seen. Once we have a profunctor, then we can define what it means for it to be representable on one side or representable on another side. So if we have an object of S, then a left representation of that is an object P upper star of S in E, P upper star of X in E, such that ordinary morphisms out of P upper star of X are the same as heteromorphisms out of X. And on the other side, a right representation of an object of E is an object of S, so that ordinary maps in S into P lower star of A are the same as heteromorphisms into A. And then if we have these representations, we automatically get an adjunction because we can put these heteromorphisms in the middle and make a composite natural isomorphism between Hom sets. So this is a way to characterize both functors in an adjunction by universal properties. And what we'd like to do is represent this inside of type theory so that both of our P upper star and P lower star can be described in sort of the well-behaved type theoretic style within induction and elimination rules. Now, let me summarize briefly the steps that I'm going to take to build up to dependent type theory, which is what we're really interested in for homotopy type theory. Dependent type theory is really complicated, so we can simplify it by not allowing type dependency. So that gives us down to simple type theory, number 2 here. And the semantics of simple type theory are categories with products or various terms of multi-categories. But I'm going to simplify even further to start with and talk about unary type theory, in which there's no dependency, and furthermore, there's only one type in the context. And this corresponds to just ordinary categories without even products or monoidal structures or anything like that. And I'm very indebted to Dan Licata for introducing me to unary type theory. It feels very degenerate from a certain point of view, but for that same reason, makes it very transparent to understand what's going on when we talk about things like adjunctions and universal properties. So here's our unary type theory for describing a profunctor between 2 categories or higher categories S and E. Okay, so we've got 2 different kinds of types, X and A in S and E, and then we have 3 different kinds of morphisms. Right on the left, we have the morphisms in S, which is sort of an ordinary type theory for S, and on the right, we have the morphisms in E, which are sort of an ordinary type theory for morphisms in E, and then in the middle, we have a judgment for heteromorphisms from an object of S to an object of E. And then, just like in the category H, upstairs we have composition that is sort of composition in S and composition in E and composition that's actions on the heteromorphisms. We have 3 different kinds of cut or substitution rules, sorry, 4 different kinds. So there's the first one gives us a composition in S. The second one gives us a composition in E. The third one gives us an action of the S morphisms on the heteromorphisms. And the fourth one gives us an action of the E morphisms on the heteromorphisms. Okay. So this type theory describes a profunctor between our categories S and our category E, all by itself. And then we can give it type operations that are described by introduction and elimination rules for the P upper star and the P lower star. So I'm not flashing these up there because I expect that you will immediately be able to grasp them and understand this type theory completely. But I want to point out that, first of all, they have the structure of ordinary type theoretic operations, right? So there are formation rules for each of them. There are introduction rules, elimination rules, and out of the bottom, we have computation and uniqueness rules. And at least in one case, if we sort of look at the P lower star rules, then we can see, in this case at least, that they're fairly transparently implementing this universal property. Right? That the introduction rule says that a heteromorphism into A is the same as an ordinary morphism into P lower star of A. The elimination rule says the opposite, that an ordinary morphism into P lower star of A gives us a heteromorphism into A. And then the computation rules down at the bottom say that those are inverses. The rules P upper star are a little more complicated because it's a positive type instead of a negative one, so we have a matching rule. But it's basically saying the same sort of universal property on the other side. Okay. And again, another point of putting this all up here is that they all fit on one slide. Right? They're not that complicated. You can sit down and understand them if you want to. At this point, I want to mention a couple of examples to give you a bit of intuition for what's going on here. We were motivated in our writing down this type theory by type theory from modal logic. Modal logic sort of has a lot of different kinds of modalities, but the most classical one, one of the most classical modalities is the necessity modality, which is often written as a box. This is an operation on propositions, which expresses the fact that the idea that something is necessarily true, whatever that means, and it satisfies some laws, which basically make it into a product-preserving comonad on propositions. A type theory for this sort of operation, which is sort of well-behaved type theoretically, was given by Fenning and Davies, and then Jason Reed decomposed that monad into the composite of a left adjoint and a right adjoint, and with a type theory for these adjunctions. And that was sort of the inspiration for our type theory for adjunctions, basically, type theory for profunctors, because we were also coming from the context of being interested in a monad or a comonad. We were originally thinking about the flat and the sharp monads in cohesive type theory, which is the second example that I've got down here, where we think about S, I didn't write this up there, but in the cohesive world, S is like the category of discrete sets or discrete infinity groupoids with no topological structure. And then the objects of E have some sort of topological or space or manifold or cohesive structure. And then the upper star gives something the discrete topology, and the lower star takes the underlying set or the underlying groupoid of points of a topological thing. And then you can look at these rules and then reinterpret them in terms of necessity or in terms of discreteness or in terms of any other kind of meaning that you give to your adjunction. So that was the case of a single adjunction. But as I said at the beginning, we're interested not just in single adjunctions, but in diagrams of toposes and higher toposes and various geometric morphisms between them. So we'd like to generalize that to have a diagram of these things. And it's not too hard to do that. In fact, Reed already did that in his context. We can give ourselves an arbitrary category, M, which we regard as the shape of our diagram. Here I've written that's the opposite shape because for technical reasons, the morphisms in M are going to point in the direction of left adjoints, whereas a geometric morphism of toposes generally points in the direction of the right adjoint, but that's sort of made a technical detail. And the objects of M, I'm going to think about as being sort of modes in the side of the type theory from the modal logic. So they could be sort of the true mode and the necessary mode. But you should also think about them as sort of different categories or different toposes. And then we have a type theory, which is parametrized by this category M. So we have a unary type theory, and we're talking about unary type theory for the moment still. We have a unary type theory, an ordinary one for each mode. And then we have these sort of heteromorphism judgments for each morphism. And the ordinary type theory is really the special case of the heteromorphism type theory where we're talking about identity morphisms. And so I've indicated this in the notation. And then we have cut rules, which generalize the cut rules that I showed in a few slides again. And we have type operations for the P upper star and the P lower star coming from every morphism in our category M, which basically satisfy exactly the same rules that I gave before, just sort of generalized to the category M. And the semantics of this, and here is where it's useful that I define profunctors in terms of a category mapping to the arrow category, because now we can talk instead about categories mapping to M. Which is now replacing our category 2 with 2 objects and 1 morphism. Now we have an arbitrary collection of objects and morphisms. Our semantics is a category H over M. The fibers over objects and identities are the categories, and then the morphisms over non-identity morphisms are these heteromorphisms or heterojudgments. And the existence of these operations, P upper star and P lower star, make this functor into an op vibration or a fibration. In the Grothendieck sense, we have sort of Cartesian arrows or op-Cartesian arrows, and if all of them exist, then we have a bifibration, and that makes it equivalent to a functor or a pseudo-functor landing in the category, the 2 category of categories and adjunctions, which is another way to think of this semantics. Okay, so this is basically what Reed described, I believe. But this isn't quite enough for what we want, because we want to think about not just the category of toposes, we want to think about the 2 category of toposes. And the reason for this is that some of the structures we're interested in, like monads or comonads or adjoint triples or adjoint quadruples, require 2 cells or natural transformations between adjunctions in order to describe them. So what we'd like to do is to generalize to letting M be a 2 category instead of a category. So we don't just have morphisms between modes, but we have 2 cells between these morphisms. And then sort of the semantics of this, we need to generalize our functor over M to some kind of fibration over a 2 category, and or bifibration. And fortunately, this already appears in the literature. So the notion of a 2 fibration was originally introduced by Hermida. Mitchell-Buckley fixed it a little bit so that it would actually be able to prove the theorem that Bakovich proposed, that it should correspond to these pseudo-functors in the way that you would expect. So first of all, we need a local condition on the Hom categories, that it has to be a fibration of ordinary categories on the Hom categories. And then we have sort of compatibility axioms with composition there. And then, so that makes it a local fibration. And then we have to add these fibration conditions if we have the P upper stars and P lower stars to describe the fibration and not fibration conditions. So I don't want to get into the details here. You can look it up. But basically the idea is we have a notion of a fibration of 2 categories, which in addition to having Cartesian and not Cartesian 1 cells, also has these Cartesian 2 cells where we can lift sort of things locally as well. And that corresponds to this kind of functor or pseudo-functor that we're interested in. So what Dan and I did a couple years ago is we generalized this general modal type theory for adjunctions to the case of where we have a 2 category of modes. And then now we have, in addition to the type theory for objects and the heteromorphisms for morphisms and the type operations, we have these structural rules coming from 2 cells in the 2 category of modes. So this comes from the local fibration condition in the definition here, where we have a 2-cell downstairs and a 1-cell upstairs. That's an object of this Hom category. We can lift the 2-cell downstairs to a 2-cell upstairs. And this gives us an action on terms which changes the parametrizing morphism of our heteromorphisms. So we have a heteromorphism over Q. We can sort of transport it along a 2-cell downstairs to get a heteromorphism over P. And this corresponds to these locally discrete 2 bifibrations, and so functors into categories and adjunctions from this 2 categories, so 2 functors here. Okay, so this is the unary type theory picture of the modal type theory, or this sort of generalized type theory for adjunctions or for geometric morphisms. So we're half done here, so maybe I'll pause for a moment and ask whether anybody has any questions. Yes?
That's the question. I mean, you don't really talk much about higher topoi. So I think what you said also, I mean, applies to ordinary topoi. And has this been sort of considered? I mean, it sort of makes also sense in sort of ordinary topos theory.
It does. I agree. It makes perfect sense for. It makes perfect sense for ordinary toposes as well, but I don't think that people have really studied this very much in that case either. I think possibly one reason is that these modalities can be a lot more expressive in the higher topos case than in the one topos case. I mean, they're certainly interesting in the one topos case, but in the higher topos case, for instance, the shape modality and cohesion, the left adjoint to the discrete to cohesion functor constructs the entire fundamental infinity groupoid of a space, of a manifold or a cohesive space. And whereas in ordinary topos theory, all it does is take the set of connected components. So it carries a lot less information. And so I think coming from the higher topos theoretic direction, we're more motivated to be able to describe modalities because they tell us more. But they're certainly also useful and interesting in the one topos case, and I think there are useful applications even in that world. That's a good question. Any other questions?
The internal universes is just in the one topos case. Like,
right.
Yeah.
Thanks. Okay, I'm going to move on. So we're going up our ladder here. We did unary type theories. Now we're going to talk about simple type theories. Okay, so if I remember a simple type theory, I mean that we allow multiple types in the context, but no type dependency. So this is like simply type lambda calculus is the sort of thing we're thinking about. So I'm going to come at this from a slightly different direction. Instead of the semantic perspective, first I'm going to talk about the syntactic version. And so instead of thinking about heteromorphisms, we can think about these heteromorphism judgments in terms of the left adjoint. So a heteromorphism from X to A is the same as a morphism from P upper star of X into A. And so the simple type theory, a way to think about that in this language is that we can allow the types in the context to be either S types or E types. So I'm going back to the case of a single adjunction. Sorry, I should have said that, which is the simpler one to understand. If the term that we're talking about lives in an E type, then we allow the domain to consist of both S types and E types, where we apply the left adjoint to our S types to, if necessary, to make them into E types to talk about our morphism. And we still have the old heteromorphism judgment, and we still have the old single category judgment, but we also have sort of these mixed judgments. The terms in S types are not allowed to depend on variables in E types. We only allow S left adjoints, like the upper star, to sort of appear in the context. And this is basically due to the asymmetry of intuitionistic type theory, where we have multiple things in the context, but not in the conclusion. And you can imagine messing with it, but that's not what we're doing right now. And you can generalize the adjunction rules that I had before to rules for this case where you have multiple types in the context. again, I'm just flashing this up here so you can see they're not that complicated. They only take one slide, and they're basically expressing a similar sort of universal property. On the categorical side, is a little bit more complicated to see what's going on. We have to replace everything by something with a monoidal structure. And in the case of ordinary simple type theory with Cartesian, with contraction and so on, we give it Cartesian monoidal structure. So our categories are now going to be Cartesian monoidal categories. Our two categories are going to be Cartesian monoidal two categories. And even the objects in our two categories are going to be Cartesian monoidal objects. By that I mean an object of a two category together with the sort of the internal structure that corresponds to sort of having finite products. So one way to say that a category has finite products is that its diagonal functor has a right adjoint for giving binary products, and its functor to the terminal category has a right adjoint giving a terminal object. And those are things that I can say internally to any two category with finite products, so that I can talk about these diagonal and unique functors, because I can talk about adjunctions inside of a two category. So our context is going to be, we have a two category, which is going to replace our category M of modes. And then the objects of this two category are going to be given Cartesian monoidal structure. And that means that M has to be a Cartesian monoidal two category. And so now, even in the case of a single adjunction, I can't just have two categories. So I can't just have two objects of M. I have to have the category, the objects that are generated by Cartesian products of those objects. So in addition to E and S, I have S cross S and E cross E and S cross S cross E cross E cross E. Then I have the product morphisms for E and S, making them Cartesian monoidal objects, like I wrote down here in the definition. And then for my adjunction, upstairs, that's going to be generated by a morphism from S to E, which is sort of a Cartesian morphism, so it preserves the Cartesian monoidal structure. And then I also get sort of composite operations here, like this morphism, like from S cross S cross E cross E cross E. First, I can apply P to those S's, and then I can take the product of any number of objects in E to get to E. And this morphism up here in my second bullet point on the top is what's going to parameterize this sort of judgment that I've got here in my first bullet point, where I have some S objects in the type and also some E objects in the type, where I apply my P upper star to the S objects. And then I can talk semantically about, I can generalize this notion of profunctor to be a category, sort of a local fibration over this two category M, which is sort of Cartesian monoidal and has the correct fibers. And this isn't strictly true because the fibers don't get quite the right thing unless you pose an extra axiom here, and or you can use multi-categories instead, which is what we actually did when we were doing this. But for understanding what's going on, I think this is good enough. You can think of, and it also helps to generalize to the dependent case later. If you think of the fiber over one of these formal product objects, like S cross S cross E cross E cross E, you think of that as being the product of these categories. So two copies of S and three copies of E, and then the morphism lying over that, we have heteromorphisms whose domain is sort of basically a quintuple or some collection of some objects in E and some objects in E in S, mapping to some object in E. And even though I didn't put in any two cells except for those going into the adjunction structure of the Cartesian monoidal structure, those two cells still have an action on the fibration condition, and that turns out to give us the sort of contraction and weakening operations of Cartesian type theory upstairs. So this is the type theory that Dan and Mitchell and I wrote down last year for sort of the simply typed modal type theory, parameterized by a Cartesian monoidal two category, or we actually use a two multi-category, where we have, again, we have a class of types for each mode, like we did before in the unary type theory. And then for every morphism downstairs in M, we have a kind of a heteromorphism judgment where the types in the context can have the modes that are specified by the domain of our parameterizing morphism downstairs. And then we have P upper stars and P lower stars for pushing forward and backward along these morphisms, and structural rules for two cells. And this has semantics in sort of these two bifibrations in sort of a Cartesian or a multi-categorical sense. Now, one reason this is really neat is because we actually get a bonus by incorporating the multi-categorical or the Cartesian monoidal structure here into the category, the two category M, because we can also, in addition to Cartesian monoidal structure on an object of M, we can also talk about non-Cartesian monoidal structure. We can give an object in a two category can have a symmetric monoidal structure or a brodated monoidal structure or a non-symmetric monoidal structure, or it could have multiple monoidal structures. It could have a Cartesian product and also a non-Cartesian product, and we can have adjunctions relating these and various kinds of structures. And so we automatically get a type theory corresponding to all those different kinds of structures that we can put on objects of our two category. And those actually correspond, with a bit of work, to type theories that people have already studied. So linear logic is basically the type theory, intuitionistic linear logic is the type theory of a symmetric monoidal structure. Ordered logic is the type theory of a non-symmetric monoidal structure. Bunched implication is the type theory of a category or an object with a symmetric monoidal structure and also a Cartesian monoidal structure that are not otherwise related. Just like box for necessity can be decomposed as a comonad induced by an adjunction, the linear logic modality bang, or of course, can also be decomposed. People have already done this decomposition as well, semantically, but we get it in terms of an adjunction between a Cartesian and a non-Cartesian object. And all these sorts of substructural type theories, or the ones that don't always have contraction and weakening, can be described as well. And so that's why this the second paper was described as a framework for not just modal logic but also substructural logic. And it's especially nice because the product types and the function types, whether it's Cartesian products or non-Cartesian tensor products or linear function types or nonlinear function types, also get unified with these p upper star and p lower star coming from these sort of adjunctions or geometric morphisms. They're a generalized sort of Cartesian monoidal or multi-categorical fibration or an opt fibration condition on this local fibration H mapping into M. I don't want to get into the details of that because it would take a while to explain exactly what's going on there. But it's sort of the fundamental structure of a simple type theory comes automatically along with the structure of these adjunctions when we express it in this way. The last nice thing here that we get here is that we can also, the two category M that we put in here to describe what's going on here. Back here I said that this two category is generated by two Cartesian monoidal objects, sort of generated freely subject to some rules. But we know we have a good way to generate categories and two categories freely subject to some rules, namely with type theoretic syntax. Type theory, the initiality theorem of type theory is really good at generating free categories. Once we can prove it. And so we can use a type theoretic syntax to generate M. So this is a type theory here, a different type theory than the one we're sort of studying. It's sort of a meta type theory or a mode type theory, where the types in this mode type theory are the modes like E and S. And then we give these modes structure, like we give them Cartesian product structure or monoidal product structure, the same way that we give a type in ordinary simple type theory a monoid structure or a ring structure by giving it operations on these types, right? So we have given X and Y in E, we get an X cross Y living in E. Given X and Y in S, we get an X cross Y living in S. Giving X in S, we get P of X living in E. This is the P operation. P preserves these Cartesian products. We have an equation between P of X cross Y and P of X cross P of Y. Then we have the diagonal from X to X cross X, which gives us, which is part of the structure for this Cartesian product being adjoint to the diagonal functor. And all the rest of this stuff which makes it work. We put into this type theory, and then M gets presented by this. And then we can parameterize our type theory back here. We can this P that goes into the term doesn't have to be a semantic thing in M, but it can also be a syntactic thing, a syntactic structure that comes from this mode type theory, this mode theory for describing the mode structure that we want. So we all sort of all get it all put into the syntax all at once. And we can imagine in modeling it, or coding it all up into a proof assistant, for instance, which would then be sort of a generic proof assistant for substructural and modal logics. And this is sort of one of my dreams, or one of our dreams, that we can have such a proof assistant once we've got the dependently typed version, so that we have all these other examples that we want. Now, what I've got down here is I claim that this is call this the type 2 theory of a Cartesian adjunction, which is written in a simple type 3 theory. And here we sort of, the title of this talk is Type 2 Theories. And so here I've got this word 2 theory first appearing here. So let me try to explain what I mean by a 2 theory. This is a little bit tangential, but I find it helpful to think about. If you get a little bit lost by the 2 theories and 3 theories, that's okay. You can tune back in when we get to dependent type theory. So in category theory, and the correspondence between category and type theory, we have what's called functorial semantics. Where in type theory, we generate a theory by types and terms and axioms, and then we build a syntactic category out of that, which is then the free category of some sort that's generated by a model. And so that means that the models of the theory, which in some other category C, which interpret the types and terms of objects and morphisms, correspond uniquely to functors of the appropriate sort out of the syntactic category. So this is sort of a classical version of this is the Levert theory of a finite products theory is freely generated by a model, but sort of the initiality conjecture for dependent type theory is also an example of this as well. Now, we actually have different versions of this for different kinds of type theories and different kinds of structured categories, right? So Levert theories are for finite product theories. Dependent type theory is for comprehension categories or categories with finite limits, various things. And people who talk about the functorial semantics, you'd like to use the word doctrine to talk about the kind of category we're thinking about, whether it's Cartesian monoidal categories or symmetric monoidal categories or comprehension categories. Each of those is a category theoretic doctrine. And the type theoretic doctrine corresponding to that is a sort of a kind of type theory where we specify the type forming operations and their rules. So something like dependent type theory with pi's and sigmas is a doctrine, or simply type lambda calculus is a doctrine, or linear logic with exponentials is a doctrine, okay, in this language. And this helps clarify things because it separates the theory, which is given by the generating types and terms and axioms, from the doctrine, which is the rules, the operations on type, the type operations and their rules. But it's a little bit confusing because often people use the word type theory to apply to both theories and to doctrines. So sometimes when people say the internal language hypothesis as saying the category of dependent type theories is equivalent to the category of locally Cartesian closed categories or locally independent or infinity one toposes or whatever, then when they say dependent type theories, they mean that each theory is a theory in the sense of this slide. It's a collection of, it's sort of generating types, terms, and axioms, or it's the object, the category of that sort, which is generated by that model. But when we say something like Martin-Left dependent type theory to refer to the judgmental structure with pi's and sigmas and identity types and so on, in the language of this slide, that's a doctrine, not a theory. Now, I mean, obviously, it's just about how we use words. We can certainly call that a theory as well, but it can be confusing to mix these levels. And so I find it helpful to think at least about there being two different levels here. Now, I'm a higher category theorist, and when I see things appearing in levels here, I tend to want to put numbers on them. Sorry, I'm going to skip that slide. And label a doctrine rather than being a theory. I want to call it a two theory, where I have type formers and rules. And I can think about that as being a structure on a two category rather than structure on a one category. And now, from this perspective, what we're doing here is we're talking about different three theories. And each three theory allows us to describe different two theories. So unary type theory and simple type theory and dependent type theory, each of those is what I call a three theory. And then inside of a three theory, like simple type theory, we can describe different two theories. And that's what we were doing before, the sort of the syntactic structure back here, where we use to present a particular two category, which describes the type operations like Cartesian products or function types or these modal operations. That's the two theory. And this syntax for here, which we've given here for presenting such a two category, is the three theory. And the point is that we can use the same three theory to describe lots of different two theories, all of which fall under the rubric of just different kinds of simple type theories. So our our progression through different versions, building up to the full complexity, is a progression through three theories. We started with the three theory of unary type theory, then we moved to the three theory of simple type theory, and now we're going to move to the three theory of dependent type theory. Okay, now you can tune back in if you didn't like the phrase three theory. Now I'm going to talk about dependent type theory. Okay, so the goal for the last 10 minutes, which is sort of the recent stuff, the new stuff, is to generalize this to dependent type theory. So that we can get things like cohesive type theory and internal universes and all of this stuff in the world of dependent type theory, where we can actually do homotopy type theory. Why is this hard? Well, why did we have to build up to it through so many stages? Well, dependent type theory is a lot more complicated because in a modal world where terms are indicated, are labeled by some sort of morphism in sort of a heteromorphism judgment, then the terms can occur in types. And so that means when I have a term that depends on via some p, the type that it lives in also has to depend via some other morphism q in some way. And moreover, the types that occur in the context depend on the previous ones via some other morphisms, R or S or whatever, and those have to be recorded somehow. And then these dependencies have to be coherent in some way that makes sense in the semantics. So as an example here, where I just have two types in the context, if B depends on A through some morphism P, and then C depends on A and B, it has to depend on them both through some different morphisms because they live in different modes, some R and some Q. And then there has to be some relationship between these three morphisms. Maybe the composite of these two equals the third one. As we'll see, it actually turns out that it's enough to have a two cell in one direction, but that's not obvious that that's the direction you want or that a two cell is enough. Or, and if you start talking about contexts with many different morphisms in them, it's not necessarily clear how to generalize this. So that's the reason dependent type theory is a lot more complicated. And another reason is that we can't, at least a priori, we can't just put them in order the same way we do in ordinary dependent type theory, right? So in ordinary dependent type theory, if B and C both depend on A, but they don't depend on each other, then I can still put them into a context in order, but just suppose that C depends on B in a trivial way. But when dependencies have to be mediated by a modal morphism, that may not even be syntactically well formed. Because if B depends on A via S, like way I've written here, and C depends on A via, B depends on A via P, and C depends on A via Q, there may not even be a morphism at all between the types in order for C to depend on Y trivially. And so the natural thing to do is sort of to structure a context, not just in a line, but with some sort of directed graph or some inverse category. And so somehow we have to build that into the syntax for our dependent modal type theory. Before I get into describing this, I want to put in a disclaimer that this is sort of a snapshot of work in progress and of what it looks like right now. And moreover, it's what it looks like right now in my head, which might be different from what it looks like in Dan's and Mitchell's heads. So you shouldn't blame them for any of this. And it might change tomorrow, and it might change again the day after that. But I want to give you some idea of at least what this sort of type theory might look like and how we're thinking of modeling it in sort of a comprehensible way. So what we did in the simple type theory case was we said our ordinary simple type theory has semantics in categories with products. And so our mode theory is going to correspond to a two category with products, a categorification of that. So an analogous thing to do for dependent type theory is to say, what is the semantics of ordinary dependent type theory? And there are various different choices for that. For now, let's choose a comprehension category. So if you're familiar with this, then you know what this is. I'm not going to describe it in detail because that would take too long. But basically the idea was we have a category C whose objects are contexts, represent context, and we have a fibration over that whose objects are types in a context, and then we have an operation, a way to interpret, to sort of to add a context to a type, to extend a context by a type existing in that context. So to get a semantic version of our our three theory for describing dependent type two theories, we'll categorify that. So we have a notion of a comprehension two category. So here now, this base is the category of context is now a two category of contexts. We have a fibration over it, which is now a two fibration, whose objects are sort of modes in a mode context. And then we have a way to extend a mode context by a mode in that context. So So here I said the way we think about these things. So the objects of M are mode contexts. So they're sort of shapes of contexts that it could have. So something like one of these inverse categories enhanced with modes and dependency structure in some sort of complicated way. Each of those things is an object of M. And then the morphisms of M are sort of substitutions between these, sort of the shapes of how such a substitution might work between contexts. The objects of D are the shapes of how type might depend on a context. So a mode like E or S, together with the information of how it might depend on the context that's given. And then the morphisms, these are shapes of terms or how those might depend on the inputs in a context. There is a little bit of that the basic two fibration is not the codomain fibration the way it is for the basic fibration, because you have to act on two cells, and that means that we have to think about the internal fibrations in a two category. And so basically what that means is that we should think about when we think about the comprehension of a mode type living over the mode context, that comprehension projection is not just a functor, but it's an internal fibration of some sense, in some sense. And that's relevant when we come to here to define what an internal comprehension object. So moving on with our categorification, in simple type theory, the mode two category is generated by Cartesian monoidal objects. Now our dependent, our comprehension two category is going to be generated by comprehension objects. My video is frozen. Can people hear me? Yeah, okay, well, I'm frozen, great. It's going to be our comprehension two category is being generated by comprehension objects. And a comprehension object, again, there's an object of M, which is like the contexts, and there's an object of D, a mode over that, which is like the types. And we think about the types as being sort of a formal fibration. And this was why we sort of matters that the basic two fibration consists of fibrations. And then we have a comprehension morphism in M, which tells us how to interpret a mode, sort of a basic mode as extending a mode context. I'm sort of trying to speed up a little bit here. So again, remember I said we want to define, we were thinking about our mode contexts as inverse categories or sort of reedy fiber diagrams, and we can describe that for any comprehension object or comprehension category. But it turns out to be easier to describe them using dependent type theory. And so what we're going to do is inside of our dependent type theory for our mode 2 theory, we're going to use sort of a mini dependent type theory to describe the modes and the mode contexts. And this looks a lot like the signatures description of inverse categories from Simonses and Weaver. But it's sort of inside of this two categorical type theory. So this is, there are different sorts of ways that you could describe the syntax, but this is an example of what a mode context might look like. So this is a context in the dependent type 2 theory for describing a dependent type 1 theory, which in this case has only one comprehension object. So let's parse this out. So these things that I've highlighted here are elements of the mode context type C, or the object C, and so they're sort of shapes of contexts, sort of individual contexts, and we're representing these by sort of mini contexts which have their own variables inside of them. So this double parenthesis is just the empty context. X in C is the lives in the context of the previous variables. The next one, the X and Y of X lives in the context of X and Y. And then each of these is an element of C, and T is something that depends on C. My fancy T depends on fancy C, and so I can apply T of these elements to get particular mode types. And so X and Y and Z, capital X and capital Y and capital Z, are variables that belong to these mode types, and I'm extending my mode context repeatedly by X and then by Y and then by Z to get my mode context. And this context altogether is supposed to describe a way in which types can depend on each other in a context. And this particular example here is the simplest one where I have of 3 types, where I have X, a type X, and then I have Y depending on X, and then I have Z depending on X and on Y with X through Y. But I can also write different kinds of inverse categories or dependency structures. So if I have capital X depending on nothing and capital Y depending on 2 variables in capital X, then that's like having 2 parallel morphisms in my inverse category. Or if I have X and Y both depending on nothing, and then Z depending on X and Y, then that's like having 2 objects and Z mapping to both of them. Or if I have Y and Z both depending on X separately but not on each other, or W depending on X and Y separately, both of which depend on X, all sorts of inverse categories can be described in this way. And this is basically the same that same way Semensis and Weaver do it. And then we get judgments in our parameterizing type theory that are parameterized by these judgments here. We have an upstairs thing and a downstairs thing, just like we did before. So let me just say quickly sort of how the two categorical, the modes come in. So if we have a mode morphism between 2 comprehension objects, then it's given by morphisms or sort of terms in this 2 theory, which can then appear in these sort of mini contexts, P of X or P of Y. And if we have a 2-cell between, down here at the bottom, a 2-cell between 2 of these morphisms, then it appears sort of as a 2-cell judgment, which can be applied to these little x's. And then that can appear here in one of these mode context morphisms to describe a morphism from R to the composite Q of P. Like I said way back when I started the dependent type theory, we need to somehow to compare these mode morphisms in order to make our context coherent. This is how that happens in the type 2 theory, with sort of the well-typedness of these actions of 2 cells on these things. And then the semantics of that gets interpreted by a pullback along this 2-cell transformation from R to QP. We have something B depending on A through Q, through P. There's a typo here. We apply Q to it, and then we pull that back along U, and then C depends on that. And this is a way, so semantically, this generates what's called an Oplax limit of an Oplax diagram, if you know what that means. And sort of that turns out to be the semantic thing corresponding to this type theory. So the idea, again, is sort of that we get all sorts of type 2 theories can be described in this syntax, and then ideally we'll be able to prove all of our meta theorems about them once and for all, so that we get a general theory of dependent type theories that have modal structure or that can represent geometric morphisms or substructural structure and all of this sort of stuff. So I think I'm finished. Sorry that was so rushed at the end there, but I wanted to at least get to talking about the transformations.
Okay, thank you very much, Mike. And I'll unmute everyone so we can talk. Okay, so now we'll just open the floor to any questions. So if you have a question, just unmute your microphone and ask Mike.
Do you think that this type theory can be implemented as a proof assistant?
You're muted, Mike. I still can't hear you, Mike.
Oh, sorry, I was muted in 2 ways. All right. Now I'm frozen. Okay. You were asking, can it be implemented in a proof assistant?
Yes. I mean, not in an existing proof assistant, but maybe as a new kind of proof assistant or whatever.
I think certainly there's a potential for that. There is some implementation already. There's a fork of Agda called Agda Flat, where there's been implemented having a single comonadic modality of the sort that they use in the internal universes paper, and kind of like the flat in cohesive type theory. And I think you may be able to axiomatize a few more in terms of that inside of Agda Flat. And so people are actually using that to formalize stuff in like the internal universes. So there's certainly the potential for implementing at least particular ones. I certainly have a dream that one day we'll be able to implement a proof assistant which is sort of parametric over the type 2 theory, so that we'll be able to first write sort of a specification of the particular 2 theory we want to work in, the particular in one file, and then sort of put that into our proof assistant, and then say, now I want, using that 2 theory, I want to work in that corresponding type theory in another file. There's certainly problems to overcome. First of all, we need to nail down the syntax, but also there's a question of how manageable it's going to be in terms of sort of manipulating the parameterizing mode stuff in the object language. So I didn't say anything about this, but with the current technology, the type theories that we get, the versions of type theory that we get out of our general framework are a little bit more complicated to use than the usual ones, because they take the usual operations and decompose them into sort of slightly more fundamental ones from the general framework perspective. So something like the contraction rule in simple type theory gets decomposed into sort of a contraction over a contraction followed by the action of a diagonal 2 cell. And so I think that ideally there'd be some sort of way to automate that in your proof assistant with some sort of tactics or sort of expression of derived rules. And so there's a lot of work to do, but I certainly have hope that in the long run, this is going to be a useful way to have sort of a generic proof assistant that could be used for all those sorts of different type theories.
I'm wondering, are there any other 3 theories that we should be aware of besides the 3 that you mentioned?
Any other 3 theories that we should be aware of? That's a good question. I don't know the answer. I mean, you can certainly think about 3 theories that have less structure. So I mentioned simple type theories, which sort of is a 3 theory that corresponds to Cartesian monoidal 2 categories. So you could also imagine a 3 theory for non-Cartesian monoidal 2 categories. Sort of that would, in a sense, that would basically just limit the sorts of 2 theories that you could express. You wouldn't be able to express Cartesian 2 theories, but only non-Cartesian ones. Actually, I take that back. I do know of another 3 theory, which is important, but I don't know of a precise description of it, which is there ought to be a 3 theory in which one can express what are called classical simple type theories, which are the ones where you have multiple types on the right-hand side of the turnstile as well as on the left. So something like classical logic or classical linear logic are often expressed in that form. And there ought to be a 3 theory which can describe all sorts of theories like that, but I don't know of a way to do it. We've thought about it some and we have some ideas, but that's sort of really up in the
air. Hello. Yes, thank you. Very, very interesting. I wonder, in the past we looked at what we call the 2-level theories. We have sort of strict equality on the one hand and weak equality on the other hand. Would this fit into this framework?
That's a good question. I don't know. I can't answer that definitely for sure, but I have the feeling that they should somehow, because so I didn't talk about this really, but the framework of comprehension 2 categories is very general, because it basically allows you to specify any kind of dependency that you can express using fibrations. So when I talked particularly about talking about comprehension objects inside of a comprehension 2 category. And those are the things that we use to talk about ordinary sort of dependent type theories with modalities on them. But I can also talk about other kinds of dependencies. So if I have, I can say, if I want to talk about first order logic, then I have a category of contexts, and then I have a fibration of predicates over that, but I don't have a comprehension operation. But I can describe that again in terms of in the language internally in a comprehension 2 category. Or if I have something like simplicial type theory or cubical type theory, where I have a category of cubes and then I have a category of faces, and then that's fibered over that, and then types fibered over that. I can talk about sort of towers of fibrations or all the various sorts of things that you find in Jacob's book on categorical semantics of type theory in terms of fibrations. And I suspect that something like 2-level type theory could be described as well by saying maybe you have one object of context, and then you have 2 different fibrations, one of the fibrant types and one of the non-fibrant types, and a map between them that interprets a fibrant type as a non-fibrant one, and then of course commutes with the comprehension or something like that. You ought to be able to recover something like 2-level type theory. Again, what you get is probably going to be more complicated in that the basic rules of 2-level type theory are going to be decomposed somehow into a few separate operations of the framework, but hopefully you ought to be able to sort of package those up into a tactic or derived rule. So I guess the short answer is I hope so. I think there's a good reason to hope so.
Thank you.
I have a question about the slide that's still on the screen. Do you expect to need hypotheses on your doctrine in order to prove these meta-theorems, or do you expect them to be very generic?
That's another good question. And that has something, it comes into the question of sort of what type operations we allow in our doctrines, and how this issue of the thing that I mentioned briefly in the simple type theory case of things like product types and function types and so on arising automatically as versions of up-Cartesian and Cartesian things. So in the simple case where we've basically proven the semantic, some of the basic meta theorems, like in that case, a cut elimination. I say we've proven, but I mean Dan and Mitchell have proven the meta theorems like canonicity, initiality, and the simple type theory case in an appropriate setting. That's where the type operations that appear in the doctrine are the ones that you get sort of canonically from the fibrational structure, and that includes sort of things like products and function types, and it also includes sort of additive operations like coproduct types, but it doesn't include things like natural numbers types and sort of inductive types. So it's not, first of all, it requires some thought to figure out how to generalize this notion of fibration to the dependently typed case. We have some ideas about that, which will hopefully include at least things like sigma types and pi types, and conjecturally, at least things like non-recursive higher inductive types. One might hope that you, at least to get them out of a framework like this, or coproduct types. I hope, at least, that in that case, if we include only these sort of non-recursive operations which are sort of arise naturally by these fibrational conditions, which then I would hope that we ought to be able to prove general meta-theorems about those. It's less obvious to me about when you start getting inductive types and recursive higher inductive types into the mix, whether you should expect to be able to prove the meta-theorems in general in those cases, whether you could even formulate a general notion of recursive higher inductive type in these cases, again, an interesting open question, but maybe you could, I don't know. It's an excellent question. Okay. I don't know, Dan. Maybe Dan or Mitchell have a thought about that.
So one thing that's a little different for canonicity than for like initiality or something like that is that so far the definitional equality in the operational semantics has just been a restriction of the Cartesian one. So if you kind of cover up all the mode stuff in the like simply typed paper, for example, then it's like what it degenerates to is just ordinary Cartesian logic. So you can think of the substructural and modal stuff as just restrictions on which normal lambda terms you're allowed to write down. And then the cut elimination behavior is just the ordinary cut elimination for Cartesian logic. It doesn't, like the terms don't run any differently than they did in the normal case. So if that's true for the dependently typed case, then maybe you can get canonicity just by kind of covering up all the mode stuff and erasing to a regular like Martin-Luff type theory term, and then like running it that way. Like the point of view is that the substructurality and the modality is sort of preventing you from doing things that you're not allowed to do in certain worlds, but doesn't fundamentally change what the terms are. I don't know about the like initiality or something like that more, since that needs to take the more precise types into account. But
Any more questions?
I have one more question. So in the motivation, you asked about describing, the situation of internal languages in the case of a geometric morphism. Another way people have been thinking about this, maybe Steve Vickers and others, is about geometric type theories. What do you think of the connection between your work and works on geometric type theories and constructions that are preserved by the inverse image functors of a geometric morphism?
That's a good question. I don't have off the top of my head exactly what is meant by a geometric type theory. I mean, so there's sort of the ordinary internal logic of a topos as a geometric fragment. Is that the sort of thing that you mean?
Yeah, exactly. So the kind of constructions that you have already, but that are preserved by the inverse image functors.
So I think the natural formulation of the rules for these things like product types and coproduct types and sigma types and so on in the dependent type theory or the modal type theory that we get has the consequence that all these sort of left adjoint things commute with each other. So in particular, these sort of left adjoint colimits and unions and tensor products are going to be preserved by the inverse image functors because they're the left adjoints. All these sort of these F types of left adjoints commute with each other automatically. You get that automatically from the rules, and they also preserve the left adjoints also preserve whatever structure is built into the domains of your three theories. So in the case of simple type theory, the left adjoints preserve finite products. In the case of dependent type theory, the left adjoints preserve finite limits, at least in the naive way of doing it. I think there are fancier things you can do to talk in dependent type theory to talk about morphisms that don't preserve finite limits, but in sort of the naive way of doing it, they do. So in a sense, I guess maybe my answer is that the geometric constructions that are preserved by inverse image functors are there as sort of the left adjointy part of the Cartesian structure that we get in the vibrational framework and are sort of automatically preserved by the inverse image functors the way they're seen in this framework.
Yeah, hello. I have a bit of a tangential remark about one of your philosophy slides, so the first one. There you say, yeah, oh yeah, we can get it up. No, even earlier. So.
Oh, way back.
Where you compared generally category theory with type theory.
Yeah.
Because
here?
Yeah, there. So yeah, it seems that there's a very strict view here where you have beta and eta rules. So I mean, this hardly applies to all type formers, for example, for equality types, not. So isn't there a refinement necessary? I mean, how do you view categorical construction type theoretically?
Are you thinking about how things like intentional identity types don't have the strict data rule that extensional ones do?
Yeah, I mean, I think it's a bit of an accident that pi types have a strict eta rule, to be honest. So they should have a weak eta rule and a strong beta rule.
Yeah, I think I'm sort of talking rather very vaguely here, but I think I would include in this correspondence typal or propositional eta rules, and that sort of happens naturally and corresponds to sort of higher categorical structure, right?
Yes,
so
yes.
In a homotopy type theory, things like coproduct types and higher inductive types and so on, we don't give them definitional eta rules, but we can prove their propositional eta rules. And so similarly, we have universal properties up to equivalence rather than up to equality. So I think it sort of carries over roughly in that sense.
Okay, well, I think what I'd like to do is try a little experiment. So first, let's thank Mike again. Okay, and I'll mention that in 2 weeks we have Martin Escardo speaking. And so I'm going to stop the recording.